Now we are going to discuss the dimensional analysis in this video. This is very interesting topic because by using the dimensional analysis, first you can guess or predict the relation of a quantity with the other quantities. We will discuss this in a moment. Second, you can verify if the relation of a quantity with the other quantities is correct based on the dimensional homogeneity. A practical consequence is that any equation must have the same dimension in the left and right side. First of all, let me remind you again about the dimensional symbol of each fundamental quantity. So, the capital M is for mass, the capital L is for length, the capital T is for time, theta is for temperature, the capital I is for electrical current, capital J is for luminous intensity, and the capital N is for the amount of substance. In the earlier days, our understanding of the physical world was heavily influenced by some great philosophers. This is the picture of the School of Athens by Renaissance artist Raphael. This picture illustrates the academic activity of the school, and the center figures here are Plato and Aristotle. Aristotle has established what is called Aristotelian physics. He believed that the Earth is the center of the solar system. The Sun and the other planets move around the Earth. This idea is called the geocentric model. Further, Aristotle also believed that the heavier object will fall faster than the lighter one. But later this one turns out to be not correct. However, without Aristotle's physics, there would have been no Galileo. So, according to the legend, Galileo tested the falling object by climbing up to the balcony of Pisa Tower and dropping two objects with different masses. These two objects hit the ground at the same time. However, the story tells us that physics is a science that needs to be verified by an experimental proof. So there was a famous clip by Apollo 15 astronaut who dropped the hammer and the feather on the moon. It was observed that the hammer and the feather hit the moon's surface at the same time, regardless their masses. Now we are going to see the dependence of the time for falling object to the ground. So suppose the traveling time of an object depends on the mass, the initial height, and the acceleration of gravity. Now, by using the dimensional analysis, we are going to determine this relation. Here we can write the traveling time is equal to a dimensionless constant k times mass to the power alpha, and then initial height h to the beta, and then the acceleration of gravity g to the gamma. Our goal is to find the values of alpha, beta, and gammas. So now we will see the dimension of these quantities. First, Here we have time, and it's obvious that the dimension is t. And then, since this is the dimensionless constant, we don't need to worry about the dimension. So we can write the next quantity. This is the mass, m, to the alpha, and then h is the initial height, that's the distance. So we can write the dimension is L, and then the acceleration of gravity, it has the units meter per square second. So the dimension is L t to the minus 2. So now let me calculate the right side first. This is m alpha, and then L to beta plus gamma, and then t minus 2 gamma. And now let's see the left side. Here we have t, and we can write like this, t to the 1. And also we can multiply here with 1. So why we need to do that? Because I want to change this 1 into dimension L here to the 0, and then m to the 0. So now, in order to have the same dimension for the left and right side, the dimension of these sides must the same. So first, for m at left side we have 0, and then at right side we have alpha. Therefore, the value of alpha here is 0. And then the L here at left side we have 0, and then at right side we have beta plus gamma. But we cannot find the value beta and gamma since we don't know both of this. But we still have one last dimension t here, and this is 1, and this minus 2 gamma. So from here we get the value of gamma, and it's minus 1/2. And from this value we can find the value of beta, so that beta here is 1/2. So now we can write that the traveling time t is equal to the dimensionless constant k times m to the 0 times initial height to the 1/2, and then g minus 1/2. The important thing here we get from our dimensional analysis is that the traveling time is proportional to the square root of initial height h divided by g. So the important thing we get here first is that the traveling times is independent of mass. And second, the traveling time is proportional to the square root of initial height. So suppose you drop an object from 1 meter, and then you also drop an object from 4 meter. Therefore, you will get the time traveling for this case is twice than the traveling time for this case. And the last thing is that the traveling time t is inversely proportional to the square root of g. So if you go to the place where that has the smaller gravitational acceleration, for example, if you go to the moon, you will get that the traveling time for the falling object will be larger than the traveling time if you drop the object on the earth. Alright, now, when Galileo was young, actually his father sent him to medical school. But Galileo's desire for science keeps him to observe many physical phenomena near him. One of these phenomena is the chandelier at the city's cathedral. He observed that the swinging time of the chandelier, measured by his own pulse, is independent from the arc of the swing. This is the second problem that we will discuss using the dimensional analysis. Suppose that the period, the time in which the chandelier completes one trip back and forth, depends on the mass, the length, and the acceleration of gravity. Now, let us determine the relationship using dimensional analysis. So now let us write the period time of the chandelier is equal to the dimensionless constant k times the mass to the alpha, and then the length of the chandelier times beta, and then the acceleration of gravity times gamma. Some of you probably will ask why we need to write the dimensionless k. I will tell you about this shortly. So first, let's us see the dimension of these quantities. First, since this is dimensionless constant, we don't need to worry about this. And then this is mass, so m to the alpha times L to the beta, and then G, here is LT minus 2 to the gamma. So here we get M to the alpha, and then L to the beta plus gamma times T minus 2 gamma. And since the period is the time for the swinging chandelier to complete back and forth, we can write this dimension here t and to the 1 here. And also, like the previous example, I can write here multiply by 1 and 1, and then we can write this L to the 0 and mass m to the 0. So now let's see the dimension of the left and right side. For m, here we get for left 0, and then the right here we get alpha, so that alpha is 0, and L here we have 0, and then here we have beta plus gamma, and T here is 1, and here is minus 2 gamma. So from the third equation here, 1 is equal to minus 2 gamma, so that gamma is equal to minus 1/2. Therefore, we can put the value of gamma so that we can get beta here is 1/2. And now we can write that the period is equal to dimensionless constant k times m to 0 times the length of chandelier to the 1/2, and then g to minus 1/2. Alright, now I can write like this. So k here is the value that we can find from the experiment. So from experiment, or also you can find that from theoretical calculation, the value of k is 2 pi. And then we can multiply here with the square root of L, the length, and divide by G. So similar to the previous example, that the period basically is proportional to the square root of the length of the chandelier and divide by G. So basically, if you have, let's say, 1 meter chandelier or pendulum, and you can also have the second one here, 25 centimeter. So the period of this pendulum or chandelier will be twice than the period of this pendulum or chandelier. So that's the interesting from what we get from the dimensional analysis. The third problem we will discuss is the force of the circular moving object. Suppose the magnitude of the force depends on the mass, the speed, and the radius of the circular path. Let us now determine the relationship of these quantities by using the dimensional analysis. So now let me write that the force here is equal to dimensionless constant k times the mass to the alpha, the speed to the beta, and then the radius to the gamma. Now we already know that this is a dimensionless constant, so we don't need to worry. And then this is mass, and this is speed. As you know, speed has units meter per second, so the dimension will be Lt to the minus 1. And then this is the radius that has the units meter, and the dimension is L to the gamma. So now we have m to the alpha, L to the beta plus gamma, and t to the minus beta. So how about here for dimension of force? So when you study the Newton law, you will know that force is equal to mass times the acceleration. Basically what I'm saying here, that the force here has the dimension of mass, kilogram, and then the acceleration, meter per square of second. So the dimension of the force will be m L t to the minus 2. So here I can write m L t minus 2, m to the 1, L to the 1, t minus 2. So now let's write again for the dimension of left and right side. For m we have 1, and then we have alpha, therefore alpha is 1, and then L, here we have 1, and then here we have beta plus gamma, and the dimension here t we have minus 2, and then this is minus beta. So from here we have beta is equal to 2. And by putting this value, we can get the gamma is minus 1. So by putting these values together, we get that force is equal to dimensionless constant k times m to the 1, and the speed to the 2, and then the radius r to the minus 1. Or by using values of k is equal to 1, that the force of an object moving in the circular path we get here is m times v here square divided by r. Now we will see the second thing that we can learn from the dimensional analysis. When Galileo studied the accelerated motion of an object, he was using a track like this. And with the help of the dropping water, he measured the time. Galileo found that the distance of the accelerated motion is proportional to the square of time. Now we will verify this. You can see more detail of his experiment in this website. And also, You can see the biography of Galileo in this website. So probably you have seen this formula that the distance covered by an object when it's accelerated is equal to the initial speed v0 times time t plus half times acceleration times square of time. The practical consequence here is that the right and the left side of this formula must have the same dimension. So now the distance traveled by the accelerated object is equal to the initial speed v0 times t plus 1/2 times the acceleration a times the square of t. And we'll see that the left and the right side here should have the same dimension. So first, now let's see that the initial speed here has the unit meter per second, and then the time has the unit second. So we'll end up that the unit here is meter, and the dimension for this term is L. And then for this one, first we don't need to worry about 1/2 here because this is dimensionless constant. And then the acceleration has units meter per square of second times square of t here, so that we'll end up with meter, and for this term we get L for its dimension. And as you know, this is distance, so it has the meter, so that the dimension here is L. So if you have a formula, therefore the component of the formula must have the same dimension. Finally, this is probably the most famous formula in the universe. E is equal to the mass times the square of the speed of light. We can verify this formula, if this is correct, by using the dimensional analysis. The capital E here is the energy, and the units of the energy is joule. So 1 joule is equal to 1 Newton meter. And you already know that 1 Newton is equal to 1 kilogram meter per square of second times meter. Therefore, the unit, the dimension of joule is mL square times t to the minus 2. Now let's see the right side here. This is mass, so the unit is kilogram, and c here is the speed of light, and the speed has units meter per second. Therefore, if you square it, you will get meter square per second square. And you can see that the dimension of the right side here is mL square t to the minus 2. Therefore, we see that the dimension of the right side and the left side, they are the same. So the next video will be vector.